Hello, my name is Michael Zengel, and I'm a physics and math major.
And I'm Riley Nold, and I'm also a physics and math major.
Today, we will be discussing our research on the atomic ordering and electronic structure of X2 yttrium tin Heusler alloys, performed under Dr. Adam Hauser in the Department of Physics and Astronomy. So our presentation will begin with a general background of Heusler materials and the motivation behind researching them, and then looking at a closer analysis of the Heusler material structure, following through with a focus and methods of our specific research, and finally ending with the results. So to begin, what are Heusler alloys? Heusler alloys are an intermetallic crystalline material, which essentially means they are a material that forms with a crystal lattice that has metallic properties. More specifically, Heusler alloys are composed of two transition metals, one repeated twice, and one main group element. Within this study, we will be looking at the X2 yttrium tin materials, where the X site is composed of any 3D transition metal, as is shown on the periodic table. As for the motivation for studying these materials, there exists a gap within the selection of materials for certain magnetic and electronic properties in both industry and research purposes. Thus, a major aim of this group is to generate a database of these materials sorted by magnetic and electronic properties for easy searching. Some of these interesting properties are shown here, one being half metallicity. Within half metallic materials, one spin is heavily favored over another during conduction. This means that in addition to an overall electric current throughout a material, there's also an overall spin current. Another interesting property is ferrimagnetism, which is an anti-alignment of adjacent magnetic moments. However, there's still a dominant moment overall. So real-world applications of these properties are high-speed transistors, which have applications in communications and high-performance computing, thermoelectrics, which convert thermal energy to electric energy, and spintronics, which utilize spin as another degree of freedom to increase the storage capabilities of memory storage devices. All three of these are vital to the development of novel technologies.
In order to contextualize our later results, it's important to understand a little bit more about the crystalline structure of Heusler materials. If we zoom in on a crystalline unicell of an ideal Heusler alloy, we see that they form in an ordered fashion known as a face-centered cubic structure. And while there are many atoms within this unicell, we can actually model the entirety of the crystal by simply looking at the ordering of the X, Y, and Z type atoms along the main body diagonal, also known as the 1-1-1 diagonal. In our research, we isolate two specific orderings, known as the L21 full Heusler and XA inverse Heusler phases. For the full Heusler phase, we see that there's an XY, XZ ordering, whereas for the inverse Heusler phase, there's an XXYZ ordering. Another way that you can view this is that the difference between the two phases is a swapping of the X2 and Y sites, and understanding the difference between these two phases is an important property of our research. So now we'll move on to a little bit more of our research focus and the methodology that we use. Specifically, our group uses a computational approach known as density functional theory in order to simulate these materials. This is done in an open source package known as Quantum Espresso. And once we've done these calculations, we can look at all sorts of important properties, such as atomic ordering, the formation energy of these different materials, and their electronic structure. As we go into a little bit more about what quantum espresso actually does, it uses a method known as a self-consistent process. Essentially, in order to understand the properties of a material, we have to know how the electrons are distributed throughout it. But in order to do this, we have to solve a formula known as the Kohn-Sham equation. However, the Kohn-Sham equation depends on knowing where the electrons are distributed. So to solve this paradoxical problem, we make an initial guess of where the electrons are distributed, plug this into our formula, and then we get out a new next best guess of what the electrons are doing. We keep plugging this back in until our all-electron wave function is converged, and from that we can get all the important properties that we need. As we go into some of the results of our research, let's start with some structural findings. So, as we vary the Xi element choice along the 3D period of the transition metals, we calculate what the difference is in cohesive energy for the two possible phases, the inverse and full Heusler, to see which one is more energetically favorable. We find that for scandium through vanadium, the XA phase is slightly favored, whereas from chromium onwards, the L21 full Heusler phase is the more favored phase. This shows that there's a clear phase transition that occurs around the vanadium to chromium region. We also look at what the ideal lattice constant is for these materials as we vary the Xi element choice for both the full and inverse Heusler phases. We find that in the region from cobalt to nickel, there is a minimum in the lattice constant that occurs. You can think of the lattice constant as essentially a measure of the size of a unit cell of our crystal for that specific element choice. We also tracked what is happening for the local magnetic moments for each element of our material as we vary this X site and for both phases. We find that for both the X1 and X2 sites in the L21 and full Heuser phases that there's a large peak in the magnetic moments, sitting around the X equals manganese region. This implies that much of the magnetic behavior of our material is dominated by our choice of the 3D transition metal that sits on the X site. We also find that along the region where we transition from the XA to L21 dominant phase, there's a flip in the sign of the yttrium magnetic moment. This implies that as we see this phase transition, there's also the induction of ferromagnetic behavior in our material, meaning that there's a large coupling between our structure and our magnetic behavior.
Now, moving from magnetic properties to electronic properties, we begin with a discussion of the density of state calculations. Density of state calculations return the number of available electron sites that exist at a specific energy within the material. More specifically, these density of state calculations are spin resolved, which means that there's a clear distinction between spin up electrons and spin down electron states, as you can see in the graph here. Also to note, on our graphs, the zero energy corresponds to the Fermi energy, or the energy of electrons conducted through the material. Now, more specifically on this graph, you can clearly see that in the spin down state, there is a certain number of electron states available. However, in the spin up state, there's a lack of states. We call that, in the spin up state, a valley of states, while in the spin down state, there's a peak. Applying these concepts to the series as a whole, we see a very clear trend where these corresponding density of state peaks misalign as we move along the series, and eventually realign. Now, this indicates an asymmetric filling of these spin states. And thus, through the artificial movement of the Fermi energy done through, say, substitutional doping, which is where we dope with a different material to artificially move this Fermi energy, we can tune the spin gap of these materials to generate half-metallic materials for uses in various applications. And without any doping, chromium-2 yttrium tin is already spin polarized enough to generate this half-metallicity.
In summary, our results provide some important characterizations of the X2 yttrium tin system. To begin, we find that the L21 phase is dominant for most Xi element choices. However, there's a clear phase transition as we move from X equals vanadium to X equals chromium. Along this region where we see the phase transition, there was also induction of ferromagnetic behavior, and also as we saw from the density of state calculations, there was a formation of a half metallic gap in this region. This implies that many of the key properties of this material system can be tuned by our choice of our Xi element, which leads to wide-ranging applications in novel electronics.
And these are our contributing sources, and we'd like to thank the National Science Foundation for funding this project, Dr. Adam Hauser, our PI, Ridwan Nahar and Dr. Strange Law, two graduate students who aided with the analysis of these materials, and Justin Lewis and Thomas Roden, fellow undergraduate researchers who contributed to the calculations done within this study. And now we'd like to open the floor for questions.
So in this project, you talk about like the material properties of the alloys that you are studying, but how can you double check that the material properties that you discuss match the properties when you apply it to the real world?
Well, another part of this study eventually will be the growth and characterization of these materials. So essentially, using a DC magnetron off-axis sputtering method, we will grow these materials in thin film form. Then, through XRD or X-ray diffraction, verify that they exhibit the structural properties we predict. And then through a physical property measurement system, we will check if they have the electronic and magnetic properties that we predicted.
For your Y and Z sites, why were yttrium and tin chosen, like over some other combination of elements?
So that's a good question. For tin, it's relatively easy to come by. So when we want to test these properties in an experimental setting, it's usually more easier to test these type of Heuser alloys than some more exotic element. However, yttrium was chosen because after literature search, we found other groups were able to show ferromagnetic behavior in yttrium-based Heuser compounds, and we wanted to see whether or not we could reproduce that behavior in our calculations.
So throughout the presentation, you mentioned that there were like two distinct structural phases. How do you know that it wouldn't form like a different type of phase?
So in short, it's not entirely certain. These calculations do assume a perfect crystallinity. However, by the control of certain environmental variables when these materials are grown, we can ensure that this primary structural disorder, the site swap disorder, is the primary mechanism of structural properties within this material.